Hello, hello. Welcome back, everyone. This is the undergraduate seminar. We're going to introduce Alex Teeter, who will tell us about the classification of surfaces. We think this might be the first undergrad talk by an undergrad. Alex, take it away.
Okay, so hello, welcome to my undergraduate seminar. I'm Alex. I'm an undergraduate at UTSC. I specialize in math and I'm also a CS major. But enough about me. Today we're going to go over the classification theorem of surfaces, a really beautiful theorem in algebraic topology. And we're going to be giving a very elementary sort of geometric proof. So I'll go right into it. So let's start off with some motivation of why we want to classify things in the first place. So an important goal in mathematics and mathematical research is to come up with sort of distinct examples of different mathematical objects and structures. So groups, manifolds, vector spaces, depending on what kind of structure you want to study, you want to be able to find, oh, when are they the same and when are they the different in respect to the structure we're looking at. And sometimes if we can understand this structure well enough, we can sort of make an infinite list that sort of goes through each object. And if we have an object, we can decide which one it is on that infinite list. So for example, if you've taken linear algebra, you probably know the classification of finite dimensional vector spaces, which says that every finite dimensional vector space over a field F is isomorphic to one of these spaces. So obviously the zero-dimensional vector space, the trivial one, or some copy of Fn. And also, if you take in group theory, you might know that every finite cyclic group is basically structurally the same as Zn, and I'll explain what structurally the same means in a sec. So, what do we mean by structurally the same, right? So I'm saying these things, but like, what do they mean, right? So let's make this precise. So we say, I'm going to give a definition here. So we say that an isomorphism is a bijective transformation between two mathematical objects that preserve structure. So bijective preserves the size, and then we also want it to have an additional property where it will preserve some sort of mathematical structure. So the structure can be different depending on the context. For instance, an isomorphism in linear algebra would just be a bijective linear transformation because linearity is the structure we want to preserve in the context of vector spaces. And then we can say that two mathematical objects are the same if there's an isomorphism between them. So now we're going to talk about invariants. So proving equivalence is a relatively easy task. You just have to demonstrate an isomorphism between your two objects. But the problem comes in, oh, well, how do we show two objects aren't equivalent? Because you'd have to check through infinitely many isomorphisms and show that, or infinitely many like transformations and show that none of them are isomorphisms between your space, which is, as you know, impossible, right? You can't check infinitely many things. So finding invariance is sort of a solution to this problem. So what invariant is it's just a property of the object that's preserved under isomorphism. So if you know if two objects are isomorphic, they must have this property. And so we also know that if two objects don't share the property, then they can't be isomorphic. So the invariants sort of help us distinguish between whether two objects are the same or different. So for example, some invariants you might know about, so the number of basis elements in a vector space is an invariant, right? Because if one vector space has two basis elements in a basis and one vector space has three, they definitely can't be isomorphic, right? They have to be different vector spaces. And the order of elements in a group is also invariant under the group. So you can't have the order of elements changing under isomorphism, under group isomorphisms. So yeah. So with the motivation out of the way, let's get into actually like defining, okay, what is a surface, right? So a surface is sort of like a set that locally looks like so locally around every point, it will look like a subset of the plane. So you probably think of the surface of the Earth, right? If you're standing on the Earth, it looks locally planar, right? So that's probably why a lot of people thought the Earth used to be flat a long time ago, because it used to be like, they used to just view it as, oh, everything's flat here, so it must be globally flat. But the difference between like a surface and a plane is that locally it's flat, but globally the structures might be much different. So yeah, here's the definition I just went over. So there's a small region U that around every point that is isomorphic to the plane. And I'll go into what we mean by an isomorphism in the context of surfaces soon. But just for now, think of isomorphic to some subset of R2 as just being, oh, it looks like the plane locally. So these are going to be the objects we want to classify, or at least a nice subset of them we're going to classify. So let's go over some examples because these will motivate our intuitions about the objects. So let's look at some examples. So the simplest example is the sphere, and you might have seen this in a multivariable calculus course. It's simply just the subset x, y, z, where x squared plus y squared plus z squared equals 1 of 3D space. And then you have the torus or the donut surface, and you can actually think of this as like a product of two circles because you have a circle around here, and then you have another circle like for every point on here. So if you sweep it out, you'll get a torus, and then we can generalize to a two-hole torus or an n-hole torus. And something to note is that it's not filled in. So keep in mind, it's not like a donut where like it has the inside filled in. I like to think of it more as like an inner tube at a water park. So it's hollow on the inside, but it has stuff on the outside. So now we're going to discuss some non-orientable surfaces. So not all surfaces are nice as the sphere or the torus. So some are what we call non-orientable. So basically we'll say a surface is non-orientable if you can take a normal vector on the surface and invert it on the surface. So what an orientation is, roughly speaking, is sort of a choice of like what side of the surface you're on. And you sort of make that choice by choosing a normal vector. So for the torus, we can see that we can choose two normal vectors and we can never slide one into the other. But if you look on a Mobius strip, if you take this normal vector and slide it all around, you'll get back to this normal vector on the other side. So we say it's non-orientable because there's not really a consistent choice of normal vector that you can choose. So you can't really pick an inside or an outside. There's no like notion of inside or outside for the Mobius strip. So as you can see right here, right? So only one side allowed for the cheat sheet. Well, no problem. Just turn your paper into a Mobius strip. Don't get any ideas.
Albert has an idea.
So here's even a weirder non-orientable surface. So the Klein bottle, you can think of it as two Mobius strips glued together along their boundary. Now this sort of pictorial representation is kind of a lie because the self-intersection here doesn't actually exist. It only exists if you're viewing it as a subset of R3. In R4, you can sort of lift it into the fourth dimension so that the intersection doesn't exist. In sort of the same fashion where if you have like two lines in the plane in 3 dimensions, you can lift one line over the other in R3. But there is another way of looking at this that's a lot easier. So there is another way of looking at this that's a lot easier. And you can look at it intrinsically. So intrinsically, you can view the surface as a space in its own right, or you can view it as a subset of Rn. So right now, I'm showing this as a subset of Rn, but we can also view this as a space in its own right. And I'll sort of show you how we can do this. So again, as I stated, it's non-orientable. You can verify this for yourself. So you can take a normal vector and then slide it around to the opposite one over here. Assuming this has no intersection. So we're thinking this intersection doesn't actually exist. So you'll have to use your imagination a bit because we can only view this thing in 3 dimensions. Obviously, we can't view 4-dimensional space. But how we can view surfaces intrinsically is we can view them as sort of a square or a rectangle with the opposite sides identified. So how you can think of this is you're gluing a square together, right? And you're thinking of these points as glued together, or more rigorously, if you know what an equivalence class is, you're taking an equivalence class of the points on this side and this side, which sort of has the effect of gluing them together. And we call these polygons, the surfaces, fundamental polygon. So here's an example of doing this with the Klein bottle. So you can literally just view the Klein bottle as this rectangle with these sides identified like this. And I should also note that when we're gluing it together, the arrows should match up. So the arrows sort of tell you how to paste the fundamental polygon together. So they're sort of the rules for the gluing. Okay, and then here's some more fundamental polygons for some surfaces. So here's the Klein bottle, obviously, which I showed in the last slide. This is the torus. So believe it or not, this is equivalent to the donut. If you glue this together with the opposite sides matching up and you make the arrows match up, you will just get the torus. And then here's the sphere as well. So again, if you do the gluing of the polygon, you will get a sphere. So here's another example of a non-orientable surface. So this is called the real projective plane. So right here, here's sort of a representation of the surface placed into three-dimensional space. It has the same problem as the Klein Bottle, where if you put it into three-dimensional space, it has to self-intersect itself, but the actual object does not have a self-intersection. So again, if all that higher dimensional stuff is confusing, you can just view it as this fundamental polygon with the sides glued together with this rule. So, and you can also view it too as a Mobius strip glued onto a semi-sphere, because all you need to do is identify the boundary of the Mobius strip to the semi-sphere, and you'll get something that looks like this. It will have a self-intersection in 3D space, but we're thinking of gluing here as gluing abstractly. And another way you can construct this too is you can take the set of lines through the origin and consider them points. So you can also construct this through taking lines through the origin, and you sort of treat these lines as like elements, and that will actually give you your real projective plane as well. So there's many ways to construct this. And it was also an object that was really important in projective geometry as well, but we're thinking of it as a non-orientable surface. We don't care about all the geometry stuff. And you can also, so there's another way to construct this too. You can view it as gluing the sides of a semisphere together diametrically. So if you can also think of it as gluing this side and gluing this side, and then identifying this side with this side. And if you take it apart, you can see that this is a valid construction. So many ways to think about this object. If one way is confusing, you can sort of think of it in another way. So we have many examples of surfaces now. That's great, but we still need a notion of equivalence, because to classify something, you need to know when they're the same and when they're different. So let's fix this. Let's define a notion of isomorphism between surfaces, and we'll call it a homeomorphism. So a homeomorphism, sorry, I apologize. That arrow should be going this way, but a homeomorphism between two surfaces is a bijective continuous function. So I'm not going to go into the nitty-gritty of what continuous function means, but I'll basically say it preserves the intrinsic topology of the surface. So the way the points are connected to each other, not in a geometric sense, but in a sort of, you can stretch it out like rubber and you can deform it, but as long as you don't tear holes in it or add holes to it, you're fine. So I should note too, so the study of surfaces under homeomorphism is a part of topology, and topologists in general study spaces in the way I just described. So as sort of rubber, so you can stretch them and bend them, and you can do all sorts of things with them, and you still consider them the same object, but you just can't puncture holes or change how the surface is connected. So here's the classic example. It's the donut to a coffee cup homeomorphism. So again, the points are still connected in the same way. Again, we did change the geometry of the surface, but again, you could probably see how you could deform the coffee cup into the donut, right? So their topology must be the same. So this is an example of a homeomorphism.
The picture on the right, or the picture on the left, sorry, was done by a guy, Henry Siegerman. He does all kinds of cool 3D printing stuff.
Yeah. And
he's coming to a conference I'm organizing, so stay tuned.
Yep. So here's another example. So the sphere, which we went over, is homeomorphic to an ellipsoid, and you can map it to an ellipsoid using the radial projection function. And if you see, this doesn't really change any part of the intrinsic topology. All the points are stretched out, but we haven't changed the way they're connected. They're still connected in the same way. And notice also it's a bijective function too, which you could verify if you were to construct an explicit radial projection mapping. And here's another example. So you might object to this. So here's a knotted torus to torus homeomorphism. So you might object to this because we are taking it apart, but we are still connecting the points back to each other in the same way they were before in the end, so in the image. So we actually do not care about whether we're taking apart the surface in the middle of the transformation, as long as at the end of the transformation, all the points are connected together in the same way. So technically, this is not a homeomorphism of surfaces, but I decided to sort of jog your intuition. So you can define a homeomorphism from R2 itself as well in sort of a similar manner. So this would be an example of a non-homeomorphism between the real line and the real line, because, well, we took the real line, which was connected, and then in the image, we tore it apart. So now it's broken into two pieces. So this piece and this piece. So we didn't really preserve the topology of the real line. We broke it apart. So we would say this is not a homeomorphism. And as well, if we took the torus and we took a piece out and then we expanded it into a cylinder, this would also not be a homeomorphism, because in the image, it's not connected in the same way it was in the pre-image. Okay, so now let's go into triangulations. So this is a technique we can use to develop invariants of our surfaces. Remember, we said invariants are a very useful tool for classifying mathematical objects. So we say a triangulation of a surface sigma is a collection of triangles tau, such that the union of the entire surface is all of the triangles, as you can see here, like all the triangles combined make up the surface. And also they have to be connected in a certain way. So they either meet at one edge, one vertex, or nowhere. So you can't have stuff like this where they're meeting at two vertexes, or they're sort of meeting like at a half edge, or they're overlapping. They have to obey that rule. Okay, so now we're ready to start developing some invariants for surfaces. So here's the Euler characteristic. So given a surface S, we define the Euler characteristic to be the number of vertices minus the number of edges plus the number of faces in a triangulation of that surface. Now, we don't know whether this is well defined because it might be dependent of the triangulation, but it turns out that it's not dependent. So no matter what triangulation of the surface you take, the Euler characteristic will be the same. There's a proof of this, but it will take us too far afield to try to prove it here. So we'll take this fact up by faith. And we'll also take the fact of topological invariance up by faith. But the intuition is, given a homeomorphism and a triangulation of the surface, the homeomorphism will always carry the triangulation to another triangulation on the other surface so that the triangles are connected in the same way. So we won't be breaking the amount of vertices or the amount of edges or the amount of faces. Okay, so let's go into an example of computing the Euler characteristic. So here would be computing the Euler characteristic for the sphere and the torus. Now, you might object to this because these are polygons on the torus, not triangles. But it turns out if we compute it using a polygon partition, it actually won't make a difference because, for example, if we take a polygon like this on a surface, we can always break it into triangles like this, right? And all we've done, we've added one face, but we've also added one edge. So it won't change the count. The count will still be the same because it's vertices minus edges. Or it's vertices minus edges plus faces. If the faces went up by one and the vertices went up by one, those cancel out. And here's a triangulation of the Klein Bottle. Again, it's done in the same way of the torus for convenience. And if you count up all the vertices and the edges and the faces, it will work out to 0. So you can do that for yourself as an exercise. Another invariant is orientability. So it turns out that if two surfaces if one surface is orientable and another is non-orientable, then they cannot be homeomorphic. So again, we'll take this up by faith, but the idea is that when you reverse the orientation on a surface, so for example, here would be the torus, and then here would be, sorry, this is the Klein Bottle, this is the torus. So if you see, these are almost the same actually, except on the Klein Bottle, the direction of the gluing on the bottom is inverted. So we kind of change the way the points are connected in the Klein Bottle versus the torus. So they can't really be homeomorphic. So that's the intuition. We're not really going to go into a rigorous proof right now because that requires a more rigorous definition of orientability, but that's the main idea. Okay, so finally, we're going to go on to surgery. So surgery is how we're going to construct more examples of surfaces. Yeah, so when we want to understand mathematical objects, we want to be able to construct new examples from old. So we're going to construct more surfaces using a process called surgery. So we basically glue together surfaces we already know to create new ones. So this is also an important technique in higher topology as well. So in classifications of more general spaces, they also use this technique a lot. So it's very important and far-reaching. So here's the orientable surgery. So we take a sphere and we take out two disks. And then after that, we associate or we glue on a handle, which is a cylinder, onto the place where we took out the two disks. And so here's an example. So we can also do this for multiple handles, right? So we can do this multiple, finitely many times for as many handles as we want. So for example, you could do this 3 times to the sphere, and you get a sphere of three handles. And this leads to the following definition. So we're going to call the standard orientable surface of genus N the surface obtained from sewing N handles onto a sphere. So if N equals 0, then we have this as homeomorphic to a sphere because we didn't do anything to it. It's still a sphere. If we glue on one handle, then if you notice, you can kind of shrink the sphere into the handle part, and that will give a torus. And then it's the same idea for 2 handles or 3 handles, or more generally N handles. So here's now non-orientable surgery. So we're going to do the same thing we did with handles for the sphere, except now we're going to glue on a Mobius strip. So we can't really do this. We can't really do this in 3 dimensions without self-intersection. So what happens when we try to glue on the Mobius strip so that its boundary matches up with this? We're going to get a self-intersection, but remember, we're thinking of gluing abstractly here. So we're just thinking of identifying the points so that they're considered the same point. So even though, yes, we technically have self-intersection here, if we're looking at this in a 3-dimensional sense, it actually doesn't matter because the gluing is abstract here. So we're just thinking of identifying the points. So the points on here, right? The points on the Mobius strip with the points on the boundary here, like that. Yeah. So again, we can also do this as finitely many times as we want. And this gives the definition of the standard non-orientable surface of genus N, which is the same idea as our standard orientable surface of genus N, except now instead of handles, we're gluing on Mobius strips. So here's another example of a surface called a Dieck surface. And you can either think of it as a torus with a Mobius strip or a cross cap sewed on. So the cross cap is what we get when the Mobius strip has to intersect itself. Or you can think about it as a cube with 3 Mobius strips glued on. And well, a square is just, or a cube is just topologically equivalent to a sphere. So this is the same as gluing on 3 Mobius strips to the sphere. Okay, so we're going to go over some final topological notions. So compactness, we just say surface S is compact if it has a finite triangulation. A topologist will be very angry with me for that definition, but it serves our purposes. We'll use it. We say S is a surface with boundary if it is homeomorphic to a surface with D disks removed. And we'll look at some examples. So don't worry if you don't understand what these mean exactly. I'll show some examples. So all the surfaces I've given so far are compact surfaces without boundary. So, I mean, it's pretty obvious why we want to work with compact surfaces, because we can compute their Euler characteristic. And that's an invariant, so that's super powerful. We would also like to work with surfaces without boundary, because again, we can always construct surfaces with boundary from them, because we can just take out D disk from a surface without boundary, and that will give you a surface with boundary. So we want to restrict our attention to these types of surfaces because this will make our classification program easier. So here's some examples of some non-compact surfaces. So the plane is not compact because there's no finite triangulation of it, right? You can never put triangles on here so that it will be like you'll have a finite triangulation. Just not possible because it's infinite. So the cylinder is a surface with boundary. So it has 2 boundary components. Here's 1 disk removed, and here's 2 disks removed. And you can think of this as removing 2 disks from the sphere, which we've seen already. And also here's a torus with 2 boundary components, and the boundary components are just right here in case you can't see them. Okay, and finally, So we say a surface is connected if it's in one piece and disconnected if it's not. So for example, if you can sort of like separate the surface with two like partitions right here, then it's not connected. Otherwise, it is connected. And we're going to say a surface is sphere-like if cutting along any closed curve will disconnect the surface. So for example, for the torus, it's not sphere-like because I could cut along the curve on here, and that will break it into a cylinder. But a cylinder is still just one connected piece. So the torus is not sphere-like. Okay. So here on out, we'll just think of surface as meaning compact connected surface without boundaries. So this will simplify things greatly for us. Okay, so finally, we're ready to state the classification theorem of surfaces. So the classification theorem says every surface S is homeomorphic to one and exactly one of the standard surfaces. So either every surface is topologically equivalent to a sphere with G handles, or it's topologically equivalent to a sphere with G Mobius strips glued on. So in the orientable case, it will be a surface with N handles, and in the non-orientable case, it'll be a surface with N Mobius strips glued on. So that's really beautiful because now, well, surfaces seem so complex, right? There's so many different examples of them you could probably think of, but topologically, they all fit into this nice list. So we're going to prove this. But before we prove the theorem, we need to prove two important lemmas that will help us get there. So first, lemma 1, if S is a compact connected surface without boundary, then its Euler characteristic must be less than or equal to 2. So we'll prove this. And we'll also prove that the following three statements are equivalent. So S is sphere-like, the Euler characteristic of S equals 2, and S is homeomorphic to the sphere. So we'll prove that these three are all equivalent statements. They're actually saying the same thing. Okay, so before I go on, I just want to ask if anybody has any quick questions, because I don't want to lose anybody. Yes?
Could you please take a second longer to see lemma 2, because I just didn't see it.
Oh, yeah. Sorry, I don't want to go too fast through that, because these are important. Is that good?
I just feel like I
Yep. Does anybody else have any short questions? Because I don't want to lose anybody like going too fast or anything. I want to make sure everyone's on the same board. Okay, so now we're going to go into some graph theory. So if you've taken a CS course before, or you've taken C32, you might have seen these before, but I'm going to just go over them quickly anyways. So we need to do some housekeeping and introduce some terminology from graph theory. So in the context of this presentation, we'll say a graph is a connected set of edges and vertices. So technically speaking, you can have disconnected graphs, but we only want to consider connected graphs in this case. So connected basically means that there's a path between every two vertices. So every two vertices is connected by a path. So I can basically take a path of edges to between any two vertices. And a tree is a graph that doesn't have any loops. So a loop is sort of like a path between a vertice and itself. So I could take a path like here, 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 and then back to this one. And it should be noted too, when I say path, I mean a unique set of edges such that we don't revisit any edge previously in the path. Okay, so we're also going to define what we mean by an Euler characteristic of a graph. It's very similar to a surface, except we're leaving out faces, because a graph doesn't really have like a notion of a face, because it's just vertices and edge. So we're going to prove these two lemmas very quickly. They follow pretty easily from just the definitions, but basically I'm going to prove that every tree always has one end vertex, and if a graph is a tree, then its Euler characteristic must be 1. So we're going to prove lemma 3 first. So suppose for a contradiction that a tree doesn't have an end vertex. So at every vertex, we'd have two edges coming out of it. So we'd have two edges coming out of it. And then from every vertex, we can always visit another vertex that's different from it by going along the next edge, the edge the edge opposite to the one we previously went out of. And this will visit a new vertex. And then it's the same thing for this vertex. And eventually we'll create a loop because we'll go back to the one we already visited. And well, that's a contradiction because trees don't have loops. So if this was true, then whatever we have can't be a tree. So that must be a contradiction. So proof of the lemma 4, we'll do some induction. So suppose we'll induct in the number of edges. So suppose we have 0 edges. Well, then our tree is just a point because the only connected graph that has 0 edges is just one vertex. So we must have that vertices minus edges is equal to 1 minus 0, which is just 1. And then now, assuming this is true for e minus 1, we're going to prove it equal for e. So by lemma 1.1, we're going to choose, or not 1.1, by lemma 3, so sorry, I'll change that. So by lemma 3, we're going to choose an end vertex, right? Because we know an end vertex always exists for a tree. Then removing the end vertex and the edge connected to it won't affect the Euler characteristic. It also won't disconnect the graph because it's an end vertex. So because we're removing one edge and we're removing one vertex, so they cancel out. So this will give us a graph of e minus 1 edges, which by the induction hypothesis has Euler characteristic 1. And if we add back the edge and the vertex, again, as analogously to as we argued before, this doesn't change the Euler characteristic. So a graph with e edges still has to have an Euler characteristic of 1. Not a graph, so a tree. A tree with e edges must have an Euler characteristic of 1. Yeah, so here's lemma 5. So if L is a graph containing a loop, then its Euler characteristic must be less than 1. So if L is a graph with a loop, then, well, again, from a loop, we can always remove one edge without disconnecting the graph because you can just take the alternate path above that edge. So here's an example. So if we had a graph with loops, we could always just take out the parts that give it loops. And if we just consider the red edges, that will give us the tree. And if we do this, right, so we have a new graph, L prime, if we do this, and again, the Euler characteristic of our original graph, L, will just be the Euler characteristic of L prime minus G, right, minus the amount of edges we took out, because we have to adjust the Euler characteristic. And well, that's just 1 minus G, because we know every tree has Euler characteristic 1, and that's less than 1. So thus, every graph must have Euler characteristic 1 or less. So now we're going to define in another important notion we're going to be using, so the dual triangulation. So we're going to take a surface S and a finite triangulation Q of that surface. So within the interior of each triangle, we're going to place a vertex. This will be called the dual vertex. Then between each pair of common edges between triangles, so if we have two triangles, right, we're going to place two vertices and an edge between them, right? So we're going to place an edge between their two vertices, and this will be called the dual edge. And then the collection of all dual edges and vertices will form the dual triangulation of S. And then we'll say any tree in the dual triangulation is said to be a dual tree. So a tree made up of edges and vertices from the dual triangulation. So then we'll also define the complement. So the complement K of a dual tree T is basically all the vertices, edges, and faces in our dual triangulation Q that do not meet T. So our Q is our triangulation of our surface. So it's basically all the parts of the triangulation that doesn't meet the tree. So let's just look at some images. So here you go. Here's what this looks like basically. In every triangle, we're taking a vertex, and then for every edge they meet, we're defining an edge between it. And here's what globally a dual triangulation would look like. Okay, so lemma 6, the vertices and edges of a complement K of a dual tree T form a connected graph. So note that K will contain all the vertices in the dual triangulation, in the triangulation Q, right? Because the dual tree, well, the tree is just the vertices and edges in the dual triangulation. By definition of the dual triangulation, those will never meet any vertice. So we're just going to induct on, so basically it suffices to prove that because this complement K contains all the vertices, that any vertice can be joined by a path of edges in K. So let's induct on the number of edges. So let's say n equals 0. Well, then K is just a point, right? Because, well, K will just be a point, right? So there's the point, and so they're connected, right? Now let's suppose the result is true for n minus 1. So let's give ourselves the dual tree with n edges and choose an n dual vertex x by lemma 3 because it's a tree. Every tree has an n vertex. And then we'll let xy be the dual vertex connecting x to y. And then x and y be the triangles containing x and y respectively. And then we'll let ABC be the vertices of the triangle x. So I know that's a lot, but let's look at a picture because that will probably make it more clear. So here's what I'm saying, right? So we're taking this vertex x in the dual tree, right? And it'll be in some triangle, and we're connecting it to this vertex y. Right, so we're going to let T1 be the dual tree obtained by removing x and the edge xy from T. So we're going to remove this and this vertex. So now the tree will have n minus 1 edges, and so by the induction hypothesis, its complement must be connected. So now we just add back our x, y, and x to here. But note that we didn't disconnect the complement at all, because all we're doing, well, it meets this edge now if we add it back. But remember, any path from A to C on this triangle could just be replaced with the path from A to B and B to C. So we haven't, by adding back the edge xy and the vertex x, we haven't disconnected it at all. So the complement K must still be a connected graph with respect to its vertices and edges. So that completes the proof. So, and then finally, I want to prove this lemma. So we say a dual tree is maximal if it is not contained in any other dual tree. So what we're going to prove is that a maximal dual tree contains all its dual vertices. So we're going to proceed by contradiction. So suppose that T is a maximal dual tree that does not contain the dual vertex x. Okay, so we're going to let P be a path from x to some point in T. And we can always move this path so that it doesn't intersect T at any other points. So we're going to let P be the point which P first intersects a triangle Y whose dual vertex is in T. So for sure, well, if it intersects a triangle, it has to go through the edge first. So it must first intersect some edge in Y. So again, let's look at a picture because that will probably make things a bit more clear. So we're going to let this be the first point where it intersects some part in the dual tree. So we're going to let Z be the triangle that shares this edge with Y. Note then that the dual vertex Z of Z will then not be in T. Otherwise, well, P would have to be this point instead, because this would be the first point we're meeting the dual tree. So, okay, so we have this vertex Z, right? But if we have this vertex Z, right, and then we have an edge, right? We obviously have an edge between this vertex and this vertex. Well, we can always extend our dual tree to include Z. So now we have an edge between Z and Y, right? But then if we added this edge in and we added a vertex Z, then obviously this dual tree is not maximal because it would be contained in this new tree we have constructed. So therefore we have a contradiction, and we have proven lemma 7, and we can finally proceed with the proofs of lemma 1 and lemma 2. So let's do that. But before I go on, does anybody have any quick questions? I just want to make sure I didn't lose anybody. Okay, so we're going to prove lemma 1. So if S is a compact connected surface without boundary, then its Euler characteristic must be less than or equal to 2. So suppose S is a surface in the above sense, and we'll let M be a triangulation of S. Then we're going to let T be some maximal dual tree of M, which we know exists because it's a compact surface. And we're going to let C be its complement. So this means that T contains all the dual vertices, right, by lemma 6. No, by lemma 7, and C has no faces as the complement, because if it contains all the dual vertices, then it covers all the faces. So no faces can be in the complement by definition. So by lemma 6, well, since C is just the vertices and the edges, well, by lemma 6, it must be a connected graph. Note that there's a one-to-one correspondence between the vertices of M and the vertices of C, as T will never pass through any of the vertices. So all the vertices will be in the complement. There's also a one-to-one correspondence between the edges of M and the edges of T and C, because either an edge was passed in the complement, or either an edge was passed in T, or it will be in the complement. So there's also a one-to-one correspondence between faces of M and vertices in T, by definition of what dual vertexes. So letting V1, E1 be the amount of faces and edges in T, V2, E2 be the amount of vertices and edges in the complement, and then these are the vertices, faces and edges in our M, well, then we're going to have chi of S. Well, that's just equal to this by the definition of an Euler characteristic surface. And remember, we have these correspondences that I brought up. So You have that the edges correspond to the edges here, here, and then we have the vertices correspond to the vertices in the complement, and then the faces correspond to these ones. So rearranging this, we get, well, the chi of S is just equal to this, and these are just the Euler characteristics of the dual tree and then its complement, right, by definition. And by lemma 4 and 5, well, we know by lemma 4 that every tree has Euler characteristic 1, and then every every graph must also be less than 1 in terms of its Euler characteristics. So we must have that chi of S is just less than 1 plus chi of C, which is less than or equal to 1 plus 1, which is equal to 2, which is what we wanted. Okay, so now we're going to go into the proof of lemma 2. So recall we wanted to prove that these three are equivalent. So how we're going to do this is we're going to prove the chain of implications. And this will ensure that given we know one, we can always get to another in sort of like a loop. Okay, so we're going to prove 1 implies 2. So we're going to let S be a surface in the above sense, and we're going to assume S is sphere-like, but its Euler characteristic is not 2 for a contradiction. So we're going to let M be a triangulation of S, and we're going to take a maximal dual tree of complement C like we did last time. And T contains all the dual vertices, same argument. So again, we have the correspondence between the vertices, edges, and faces on our surface, right? So we have this equality holds, right? Because of the correspondence, right? Same argument as last time. So rearranging the terms, right? We get chi of C, so the Euler characteristic of the complement is simply just the Euler characteristic of S minus the Euler characteristic of T. And T is a tree, so its Euler characteristic must be 1, right? And remember, we said chi of S is not equal to 2, right? We are assuming that for a contradiction. So the Euler characteristic of our complement can't be 1. So C is not a tree. So somewhere on C, there must be a loop, right? There must be a loop somewhere on there, right? And S is sphere-like, right? We're assuming that. So we're proving 1 implies 2. So this implies that the loop must separate S into 2 disjoint pieces by definition of sphere-like. Remember, sphere-like, any loop on the surface we take separates it into 2 disjoint pieces, right? So by lemma 6, T contains all the dual vertices in S, and T is a tree, and therefore it's a connected set of vertices and edges. So we should be able to take a path on T from one disjoint component to another that does not meet this curve at any points, because the complement never meets the dual tree by definition of the complement. But then the loop doesn't disconnect S after all, because we can take a path from one point on S to another going around the loop. Then the loop doesn't disconnect the surface, right? It doesn't partition the surface into 2 parts. So 1 must imply 2. Okay, so now we're going to prove 2 implies 3. So let's assume that S is a surface in the above sense and that chi of S is equal to 2. And we want to show that S is homeo to a sphere. So letting T be our maximal dual tree and C be its complement, we know from an analogous argument to our proof that 1 implies 2 that, again, we have this equality. And remember, right, so we have the Euler characteristic of S is equal to 2. That's what we're assuming here. So, and this is a tree. So remember, we also proved all trees of Euler characteristic 1. So we must have 2 minus 1, and that's equal to 1. So that must mean the complement is a tree. So we're going to let the neighborhood of T be a small like neighborhood around T. And we're going to claim that this neighborhood is homeo to a disk. So by lemma 3, T will always have a dual vertex. So we can continuously remove n dual vertexes from T, and it will still be a connected tree until we get down to a point. So we'll have a little point right here and like a little neighborhood around it. Then we can add back the n vertices and grow it out and make sure that the neighborhood is always like around it as we grow it out. And this neighborhood will always be homeomorphic to a disk, right? So, and we'll always get something homeomorphic to the neighborhood around T. And we'll end off, so again, we'll just grow this back out, right? And each neighborhood will be homeo to a disk, but it will also be homeo to the neighborhood around T. So by an analogous argument, right, the neighborhood around C is also homeo to a disk. Now for a point on S, we're going to let Tx and Cx denote the distances from T and C respectively to X. Now we're going to assume without loss of generality that X is on some flat triangle so we can measure distances effectively. right? We can always assume we have a flat triangulation because Euler characteristic is independent of the triangulation we choose. So locally, by definition of T and C, at least one of them is going to be on each triangle. So if we have a point in the triangle and we have some neighborhood of maybe it's n of T or n of C, we can always grow out this neighborhood to include the point, right? And locally, it'll still be homeomorphic to a disk, right? Because we didn't change the topology at all, right? So if the distance from T is greater, then we're going to expand it into n of T. And likewise, if the distance to C is less, right, we're going to expand it into the neighborhood around C. And the resulting, these resulting neighborhoods are homeomorphic to the originals. And also the points on the boundary are precisely their intersection, right? So if a point, right, satisfies both this and this, well, then both neighborhoods, we're going to grow into them. And also this is like, so the point where C of X is equal to T of X is the maximal point basically where you can actually be in this neighborhood. So it's the boundary. So it's on the very outskirts of this neighborhood. So S is simply just these neighborhoods glued along their boundary. Because remember, we did this for every single point. So every single point must be surrounded by one of these neighborhoods, right? And if these neighborhoods are just two things such that their boundaries are just their intersection and they're homeomorphic to disks and they make up the whole surface, well, S just must be two disks glued along its boundary, right? And that's just a sphere. Because if you take two disks and it looks like this, right, along the boundary, that's just a sphere. Okay, and finally, the proof of lemma 2. So we're going to suppose S is homeomorphic to a sphere. And we want to show that S is sphere-like. So remember that any curve divides it into two pieces. So we're going to consider a curve C on S, and without loss of generality, we can assume that C is a polygon of vertices and edges in S, right? Because you can always just make a curve homeomorphic to C that is just a bunch of vertices and edges. So we can choose a point on X that is not contained in C or any of the great circles containing arcs on C and consider it the North Pole. So given any other point Y that is not X or the South Pole, we consider the arc XY. We say XY has even parity if it intersects C an even number of times and odd parity defined likewise. So it'll look like this. So we'll have any point Y connected to X. We have X is here. We'll call that the North Pole. And then given like how many times a great circle arc has to intersect this curve, we'll either say it has even parity or odd parity. And we'll use this convention for this kind of intersection. Well, along any path not containing C, the parity remains constant even because we're not containing the path. So C divides S into two distinct set of points, even and odd as wanted, because, well, if we go through the curve, right, it has to be odd. And if it's inside the curve, well, we have to intersect the curve at least like odd many points, right? Either one, or we're going to have to go in and out another time to get to Y. But if it's on the outside, we don't have to intersect the curve at all. So that will be 0. Okay, finally, we're here. We're at the main event.
We have 7 minutes.
Yeah.
Including 3 minutes for question time and like filling out the surveys.
Yeah. Okay, so here's how we're going to start. We're going to take a surface S. Right? We're going to begin by letting S be a compact connected surface without boundary. So we want to show S is homeomorphic to a standard surface. So we're going to take a finite triangulation of S and compute its Euler characteristic. So by lemma 1, right, we know that the Euler characteristic of a surface must be less than or equal to 2. If tri of S equals 2, then by lemma 2, we know this is equivalent to S being homeomorphic to a sphere. So we're done, because that's just the first list in the standard orientable surfaces list. If the Euler characteristic is less than 2, then by lemma 2, S is not sphere-like, and so we can choose a curve to cut S that does not disconnect it. So we're going to consider a small strip containing this curve. So either the whole strip will be bounded by that one curve, in which case it will be a Mobius strip, or the curve will be a cylinder. So we're either cutting out a cylinder or a Mobius strip from our surface, and we're gluing on disks after. So we're going to call C orientation preserving if this is a cylinder, and orientation reversing otherwise. So we're going to construct another surface S1 from surgery again as follows. So we're going to cut out, again, we're going to basically, again, do the same process, right? Glue on disks. And also, when we cut out this strip, we're going to add on orientations to the disks when we glue them back in. so that we know where to glue stuff back in afterwards. Okay. So I claim this, right? So I claim that the Euler characteristic of this new surface we got from surgery has this property. So if C is a curve, then we have n vertices and n edges on it. So its Euler characteristic is 0. So removing, right, we're just removing the curve, right, will not affect the Euler characteristic of S. Now we break into cases. So we're going to consider the case where C is orientation preserving. Then we're going to glue 2 disks onto each boundary component we left by the cylinder. And well, if we consider gluing disks on is equivalent to joining the vertices of this curve to a point, right? Which it basically is. We're just joining the vertices to a point inside, right? We're going to have the Euler characteristic of, right? So this will add 2 n edges, right? 2 n edges, right? So the edges on here and then the edges on here. 1 vertex, or no, n plus 1 vertices, because you have the vertices around here and inside of here, and it will add n faces. So in the end, we'll just get that adding on a disk will add bring up the Euler characteristic by 1. So again, so in the orientation preserving case, since we added on 2 disks, it goes up by 2. And for the orientation reversing case, we can argue analogously, except now we're only adding on 1 disk. So we'll get this, right? Same argument. So again, this implies that the Euler characteristic goes up after each surgery, and we can argue inductively this happens every single time. So we can take now a finite sequence of surgeries, and remember, right, the Euler characteristic of a surface must be less than S. So eventually we're going to have to stop, right? Because we'll get up to a sphere, right? We'll get up to a sphere. So S of k will be homeomorphic to a sphere. Right now, what we can do is we have S of k, which is a sphere with some disks glued on. So now we can ensure each disk is disjoint by shrinking each into the interior of its triangulation. And this doesn't alter the topology. So now we have a collection of disjoint disks. So now we're going to perform D surgery. So this will just connect back the points to where they were before. So here's sort of how it will go. So either we'll have 2 disks with opposite orientations. So this will result in gluing back on a handle. We'll have 2 disks with the same orientation, where we'll have to have a cylinder now go through the surface. And this will have the effect of basically making the surface into a Klein bottle. And we'll just have 1 disk left over, in which case we'll glue on a Mobius strip. So this is a type 1 D surgery, a type 2 D surgery, and the third one we've already seen. So before. So doing these surgeries in order, we'll glue back all the points so they're connected in the same way. And this will give us a surface homeomorphic to our original. So in the first case, if S prime is orientable, well, then we can't have any Klein bottles or Mobius strips in it because those are non-orientable. So only surgeries of type 1 can occur. Therefore, our surface must be homeomorphic to a sphere with n handles glued on. And you can also compute that the Euler characteristic of this surface must be related to the amount of handles in this way. I'll leave that as an exercise. So if S prime is non-orientable, all types of D surgery can occur. But note, we can change a type 1 surgery into a type 2 surgery because this surface is non-orientable. So it must have some sort of Mobius strip inside of it. So we can take the handle and sort of slide it across the Mobius strip, and that will give us a type 2D surgery. So again, so now we have type 2 and type 3D surgeries, but note a type 2D surgery is just sewing on a Klein bottle. And as we discussed before, a Klein bottle is just a sphere with 2 projective planes on it. Yep, and again, as we discussed, you can also compute that the amount of Mobius strips on this surface is related to the Euler characteristic in this way. Thus, either we have a surface that is n handles glued on, or a surface that is n Mobius strips glued on, right? So there we go. Every surface has this form. This completes the proof. Blah, blah, blah. This is just, also you can classify a surface by its Euler characteristic and whether it's orientable or not, right? And this just follows from the fact that we have this relation between the amount of handles or the amount of projectile or Mobius strips glued on. And finally, here's some other stuff. So the techniques we used in this presentation are also used in higher dimensional topology. So I really encourage you to look up more stuff about that. Aleph 0 is a great video on the Poincare conjecture that I really liked, and it's sort of in the similar flavor to this. So if you want to learn more about stuff similar to this, that's a really good video to check out. And then here's some recommended reading. And with that, I end off the presentation.
Nice. For the folks who are watching online, I'm going to put a link in the chat. This is to give feedback to Alex on the talk. Our tradition is that we fill out this form and then do question period. For the people who are in the room, in order to get snacks, we need to fill out the undergraduate seminar form. So if you could please put your name and email. This is what ensures that we have money for coffee and other good things. So let's take 3 minutes to fill out that form, and then we can do questions and stuff. Online people, please fill out the survey in the chat. It is very, very, very helpful. Yeah, there's a sweet comment in the room that like everyone knows this joke, or you see in public school this joke about like donuts and coffee cups, and then it takes you like 10 years to actually figure out why the joke is true. Yeah. Okay, online people, thank you for filling out the form. We've got a little bit of time for questions. So yeah, if people have questions for Alex, take it away. Okay, well, thank you for coming out to this instance of undergrad seminar. Our next talk will be Ben Briggs, a friend of mine and now a postdoc, will tell us what's the deal with homological algebra. What's up with homological algebra? So we hope to see you there. Thank you for coming out. Same time, same Zoom link next week. See you, folks.